Okay, well, welcome back after the Labor Day holiday. I hope everybody had a good weekend. Um, I guess there was a little bit of confusion about the homework, and I apologize a bit for that. What I did on Friday was I quickly flashed this up here, and I didn't mean for you to have to copy it down or anything like that. And what I normally do, and I think I've indicated it in the syllabus we handed out, is that what I try to do either right before or right after class is post everything on both BSpace and the class website. Now, it turns out on Friday, BSpace was down, okay? And then I went away for the weekend, and I didn't do anything until yesterday to correct that. But nevertheless, this was up on the class website on Friday. And I hope people know how to find the class website. I didn't write down the URL, but if you go to the Nuclear Engineering Department homepage, there's a link to all the courses, and you'll find ours there, and all the lectures thus far, and the first solution set for the first homework problem are already posted there. So I'm going to stick to the idea that this homework set will be due on Friday of this week. If there are issues about it, come see us. I have office hours today and Wednesday, and the TAs also have office hours before the homework set is due, so please take advantage of that. And if you've looked at this already, you can see that this homework assignment is significantly more difficult and challenging than the first one. That's deliberate. The first one was, to sort of lull you into the idea that this is all going to be easy. But not to scare you away too much. But they're going to get more challenging as we go along. So put in the effort it's needed. If there are questions, come see us. Okay, so that's it. And what we began the discussion of on Friday was this idea of radioactive decay and how we can quantify the number of radioactive nuclei present as a function of time and what the implications of that are. And so we started with the idea that the radioactive decay of isotopes is a unique feature of each isotope in terms of how long that isotope will live before it decays and the manner in which it decays, namely whether it undergoes alpha or beta or gamma decay or some other kind of radioactive decay. And I introduced the concept of this decay constant, which is a number. It has units of inverse time. It's a rate, number of decays per second, if you like. And that's a characteristic of a particular isotope. And we can take that equation, the differential equation written there, and integrate it and get the famous exponential decay law. Okay. What I mentioned but didn't define very carefully last time was the idea of a half-life. And we'll use decay constants and half-lives to both represent the rate at which a radioactive species is decaying. So the half-life is defined to be the time required for half of a sample of a particular radioactive isotope to undergo decay. And it's related to the decay constant lambda through this expression. So the half-life is the natural logarithm of the number 2 divided by lambda. And numerically, to 3 digits, the log of 2 is 0.693, and I don't think I'll ever ask you for any more digits than that in any problem or exam. So the half-life is 0.693 over lambda. Normally, we'll talk about half-lives, and that's the definition of it. Occasionally, you'll run across another unit of time, which is also related to the radioactive decay constant. It's called the mean lifetime, okay? And it's similar to, but not exactly the same as the half-life. It's 1 over lambda. And so if you think about it, 1 over lambda is the time it takes the number of radioactive nuclei to decrease to 1 over e of their initial value, whereas the half-life is the time it takes the number to decay to 1/2 of their initial value. So they're similar, but not numerically exactly the same. We'll talk about a quantity called activity, which is the number of decays per second that are happening, or the number of decays per unit time that are happening. And that's simply the product of the lambda for that particular isotope times the number of that isotope that are present. Now, in general, that number is a function of time, so this will not necessarily be a constant. But at any given time, that's the definition of the activity. And quantitatively, we use units to describe radioactivity. The historical unit is called the Curie, named after Madame Curie, and it's an enormous amount of activity. It's 3.7 times 10 to the 10th decays per second. And the definition of this comes from the fact that that's the number of decays per second that occur in 1 gram of radium. Radium is a radioactive species that Madame Curie discovered and identified, and so it was named after her, and that's the unit that was historically used. The more modern unit is called the becquerel, named after Henri Becquerel, who was one of the pioneers in the early experiments in nuclear science, and it's a fancy name for 1 decay per second. So 1 decay per second is now called 1 becquerel. And when we're doing problems in radioactive decay, you can use either set of units, but you have to be consistent about it. So if you're measuring a radioactive species and you're telling how many decays there are per second, tell me, okay, it's X decays per second, or it's X becquerels, or it's X number of curies. But there needs to be a unit assigned to that, so we know what we're talking about. Okay, so we've introduced the concept of a half-life, and now what I'd like to do is actually do an experiment to measure the half-life of one particular radioactive isotope. And let me leave the light off for a second. So this is the kind of drawing you're going to see over and over again in the course of this semester. And so you need to start getting familiar with it. This is what's called a nuclear decay scheme. And what's being shown here is the decay of a particular isotope, cesium-137. Cesium-137 is an important isotope in nuclear engineering because it turns out it's a major fission product. So once you run your uranium through a nuclear power plant and pull the fuel out after it's been burned up, there are a lot of fission products, which are mainly radioactive, and they decay over time. And one of the relatively long-lived ones that there's a lot of is cesium-137. It has a half-life of 30 years, meaning whatever number of cesium-137s I have today, it's going to take 30 years for that number to go down to half that value, and then another 30 years to go down another factor of a half, meaning to a quarter of its value, and so on. That's a fairly long time on human timescales, but there are many other isotopes that have even longer half-lives that are fission products, and that's why we worry about how we're going to store nuclear waste for very, very long periods of time. That's why people at this university and places around the world have studied things like Yucca Mountain as a long-term repository where you could put things and have them stay there for millions of years. Okay, so we're interested in half-lives. We're not going to measure the half-life here. We're not going to measure the half-life of cesium, 30 years. That would take a long time, and you'd get bored, and I'd get old and gray. So we're not going to do that. But what happens in cesium-137 decay is it undergoes beta-minus decay. Remember we talked about that a week or so ago. What happens is cesium-137 has 55 protons in its nucleus, and therefore 82 neutrons. Okay, so that the sum is 137. And that's too many neutrons for that number of protons. So in beta-minus decay, one of those neutrons turns into a proton. That proton stays inside the nucleus, and so the Z of the nucleus changes from 55 to 56. That means you've changed from one chemical element to another. You've changed from being cesium to being barium. Okay? And a beta-minus particle, an electron is emitted, and a neutrino. Okay. The beta-minus decay of cesium-137 usually goes to not the lowest level state, not the lowest state in barium-137. It goes to what we call an excited state. Remember I mentioned early on that when you have a nucleus this complicated, 137 neutrons and protons running around inside, there are many, many different ways they can be organized and arranged. And one of them will be the lowest energy state, called the ground state. But there are excited states, and in the beta decay of cesium-137, it almost always goes to an excited state, which is 662,000 electron volts, 662 keV above the ground state. It turns out that these nuclei all have spins and parities that we talked about. The cesium-137 has a spin of 7 halves in units of h-bar and positive parity. The ground state of barium-137 has a spin of 3 halves h-bar and positive parity. And because of this relatively large spin difference and parity being the same, that decay doesn't happen very frequently. It's much more likely that it will go to this state with a spin and parity of 11 halves minus. Now this state, once it's fed by the beta decay, will gamma decay to the ground state. So this is an example of a situation where you have a beta decay followed by a gamma decay. Because of the relatively large spin difference between this state and this state, this excited state at 662 keV lives quite a while before that gamma ray is emitted. Okay? And what we're going to do today is measure the half-life of that state. And the way we do this is to make use of both chemistry and physics. Okay? The physics is the beta decay, and the fact that we have a Geiger counter sitting over there that I've already demonstrated to you can observe gamma rays. So we're going to eventually observe this gamma ray, but the trick is using a little chemistry first. And the idea is that cesium decays into barium. There are two different elements, they have different chemistries. So I start out with a source that has cesium and barium in it, because while we're sitting here talking, the cesium in that little bag over there is decaying away to barium, okay? There are two different chemical elements. They're sitting inside a little device I'll show you in a minute. But because the chemistry of barium is different than that of cesium, I can perform some chemistry and separate out the barium and leave the cesium behind. So when I do that, I end up extracting all of the barium atoms that are sitting in that sample, the ones in the ground state and the ones in this excited state. Now, the ones in the ground state are stable. They don't do anything, so our detector won't see them. But the ones in the excited state will continue their decay into the ground state, but now they will no longer be replaced by fresh decays from the cesium. And so what we'll get to see is the exponential decay of that one level and measure its half-life. Okay? And we'll try to take some data. That's what I wrote over here. I'm going to need a couple volunteers to come up and help me with this. And what we're going to do is to measure the number of these gammas every 30 seconds and watch them decay away, hopefully. Okay? So let me get set up here, and then I'll ask for a couple brave volunteers to come up and help with this. And I'll do demonstrations. I've done some already using radioactive materials. The levels of radiation and radioactivity are all incredibly low. We're not exposing you unduly to anything. It's not dangerous. I will try to be careful with this. I'll try not to spill it. I will wear gloves. There are some liquids involved here, and if you see a few liquid drops falling on the table or going somewhere I didn't intend them, it's actually okay, because the half-life here is fairly short, and even if I spill, if I wait 10 minutes or 20 minutes, it's all decayed away and it decays into something stable, so we don't have a problem. And that's why the university lets me do this here. Okay, so let me get my paraphernalia together. Okay, so we will wear gloves. You know, you have to be a little bit cautious on any radioactive material. You don't want to contaminate yourself or others. So whenever we're handling unsealed radioactivity, which is what this is going to be very soon, we always wear gloves. If there's a potential to spill it, I would wear a lab coat. Hopefully I won't be that clumsy today. Okay. Okay, almost ready. And this is all very high tech, you can see. Okay, so what I've got here, this is called a radioisotope generator. Okay, so inside this little plastic object, there's a column that contains resin. It's a plastic bead, a set of plastic beads that are coated with a material that absorbs cesium, okay? The cesium sticks to those coated beads. And if I bring my Geiger counter over here, real scale, you can hear, I'm just going to put this down. Hopefully you can hear and see that the meter is responding to the gamma rays which are coming out of that. And if I pull it away, this is really the source of the gamma rays. And if I sit here for a while and you look at the needle there, and let me just put it down so I'm not playing with it. The needle is sitting there at a nearly constant value, okay? Not exactly constant, because these radioactive decays are random events. So there is a fluctuation in the number, but if we stare here a while, it's pretty much at, on this scale, 2,000 counts a second, okay? And if I want to measure the half-life of cesium-137, which is what that meter is now looking at, I'd have to wait 30 years for that to go down to 1,000 counts a second. What we're going to do, to turn off that annoying beep for a minute, is this solution has the property that it likes to grab barium and not cesium, okay? So what we're going to do is we're going to run a few drops of this solution through this device. We'll use a syringe. I'll push the syringe down, force a little bit of liquid through the top, collect the drops out the bottom, and hopefully what happens is that liquid And for the chemists in the room, this is called this is actually sodium chloride in 0.4 molar hydrochloric acid. So it's the sodium chloride which is doing this. It's bringing out the barium and leaving the cesium behind. And what I'll do is I'll collect those drops on this high-tech collection device known as a piece of tissue paper, and I'll put it inside a plastic bag, and then we'll count it. And I put it inside the plastic bag so I don't end up contaminating my Geiger counter, because I'm going to put it right down on top of it. Okay, so we're just about ready. Let me pour out some of the liquid. So put a little bit of liquid in here. Okay. And then what I'll do is remove the top and the bottom from the generator. And I'll take a little bit of the liquid up in the syringe. Okay, so I've got my solution in the syringe now. I'm going to push it through there and collect the activity on this piece of paper. Okay, so now I'll ask for 2 volunteers to come up. One person's going to be a recorder and write down the numbers here, and the other person is going to read off the number from the meter. Don't all jump up at once. I promise it's safe. We're not going to irradiate you. We're not going to make you glow in the dark or anything like that. Are you volunteering? Okay, we have one brave soul. How about somebody else? Okay, thank you. And the other thing we need is a watch. Okay, do you have a watch with a second hand on it? Okay, if not, okay, I'll take care of that. I'll take care of it. Hang on. Exact. Well, I was just going to go to, hang on. Where was I? No. We'll eventually get this going. Okay, date and time. Yeah, that's fine. Okay, fine. Okay, so what I'm going to ask, you're going to be the recorder? Yeah. Okay, so once we get this set up, and let me show you, we're going to look at this upper scale here. Okay. The upper scale. 1K, 2K, 3K, right. So those are, K means 1,000. Okay. And what we're going to ask you to do is to do your best to read the number. Now, it jumps around a little bit, so you have to kind of average it over a second or two. What I'll do, every 30 seconds, I'll ask you to read out the number. And I'd like you just to say it so we can get it recorded. Okay? We'll do it every 30 seconds. Okay? No, you're not going to hold it. We're going to put it down so that it doesn't move. Because one of the problems in doing this kind of measurement is the detector has an efficiency which depends on how far away the source is from the detector. So I don't want to be moving the detector while I'm trying to measure its decay. So once I get things set up, I'm going to put it down and leave it there, and we're not going to want to touch it. So all we're going to want to do is read that number. Sure. Okay? Yeah. Any questions about this? Okay. So what I'm going to do, I actually want to get that out of there for a second. I don't want to spill that. I'm going to put it in the plastic bag after I do it. Okay, so I'm going to try to push out about 10 drops. That's about all it takes to get enough activity to measure. Okay, here we go. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's enough. Okay, I'm going to put this in the bag, and I'm going to seal it up. I'm going to get this away because I don't want the meter to be reading that, and now I'm going to put it there. And it counts like crazy. It's off the scale. And what I'm going to try to do is adjust it so it's about 5,000 or so. Okay, that's about right. Now, hang on a second. Okay, take a reading right now. 5.3, 5,300. Okay, and we're going to do this every 30 seconds for 5 minutes, okay? And what I'd like you to do is to keep track of this and start trying to figure out the half-life, okay, from the data that's being written here. I'll give you a little countdown. 5, 4, 3, 2, 1. Take another reading. 4,700. Okay, at least it's going in the right direction. And if you listen closely, hopefully you'll hear that annoying noise, getting less and less. Five, 4, 3, 2, 1. Another reading. 4,300. Okay, good. So it's decaying away because the cesium is not feeding it anymore. We've just got the barium in that long-lived excited state, and the detector's seeing the gamma rays from that. Five, 4, 3, 2, 1. Reading. 3,700. Half-life a day? No, it's much shorter than that. Is it a second? No, it's much longer than that. Okay, we're narrowing it in. Keep that thought. Five, 4, 3, 2, 1. Read. 3,100. Okay. So the half-life is the time it takes half the species to decay away. So we started at 5,300 or so. So the half-life will be when we get to about 2,650 or something like that. Five, 4, 3, 2, 1. Read. 2,700? Okay. Okay. For good measure, we'll keep on going a little bit because there are a few extra points I want to highlight here. Five, 4, 3, 2, 1. Read.
20.
What was it?
22.
22. Okay. More. Five, 4, 3, 2, 1. Go. 1,900. Okay. 3 more. Sure. You're checking to see that we're not cheating here. Very good. It's always good to have more than one person involved in the experiment. Five, 4, 3, 2, 1. Read. 1,700. Okay. Anybody have a graphing calculator who's plotting these data points up? No? Okay. You can do that for your homework. Oh, 3, 2, 1, go. 1,400. Okay, last point coming up. Five, 4, 3, 2, 1, go. 1.2? Okay. Thank you very much. Great job. All right, we'll shut that off. That's annoying. It's annoying, isn't it? That's a good thing because then you know something's going on. You can't forget about it. Okay, so let's look at this data. We did the chemical separation. I claimed what we were doing is pulling barium out of that source, and we measured the number of counts as a function of time. We started at an arbitrary time. That's one thing that's very important about the exponential decay law. It doesn't matter when you start, okay? So we called this time 0, but I fumbled around here for a little bit and got things set up so we had a reasonable counting rate initially, and then started the measurement. But the thing about the radioactive decay law is it doesn't matter when you start. You're always measuring the rate of change over a certain time interval. So I call this 0, and we measured something like 5,300 decays per second happening at that point. We took measurements every 30 seconds, and a half-life is defined to be the time when the number of the parent decreases by a factor of 2. So I take that number and I divide it by 2, and I would get 2650, and that comes out pretty close to that 150-second measurement. So based on that one comparison of this data point to this data point, I would say the half-life is about 150 seconds, okay? But let's see if that trend is always true. So I move down here, and I pretend I don't know about this measurement. Suppose this was when I started. I started 30 seconds. I had 4,700 counts. So the half-life is the time it takes that number to go down a factor of 2. So I'm looking for 2350, which is somewhere in between here, a little bit closer to this one. Okay? So again, I would say it's something like 150 seconds using these two data points. If I go down here, I say I start here, 60 seconds, I had 4,300. I would expect 2150, which is around here. So I would get a slightly shorter half-life. I'd say it's like 120 seconds or maybe 125 seconds, something like that. And so on. The point is that it doesn't matter when you start. Whenever you start, you call that T0 if you like. And if you're measuring a half-life, you try to figure out at what time the decay rate is half of the value when you called it T0. Okay? Now, I hope you can appreciate this is a very crude experiment we did here. It's difficult to read that meter. It's jumping around. We have much more precise ways of measuring half-lives. But nevertheless, from this set of data, we would infer a half-life of something like 150 seconds. And one of the homework assignments tonight is to go actually look up the real half-life. It turns out it's very nearly that. Okay, it's 158 or something like that. So this simple experiment lets you get very close to the true value. And the other thing I should have pointed out is, let's go back here for a second. So we started out at what we called T equals 0, 5,300 counts. What would be the activity after 2 half-lives? 1/4 of the initial value, right? It's a half times a half. So 1/4 of that is what, about 1,300? Okay. So it'll be around between 270 and 300 seconds. Again, it's consistent with 150-second half-life. Okay? Okay. So let me just spend a second. We'll leave it here. I'll clean up at the end. Okay. So that's a half-life. And one of the homework problems you've got, we'll come to in a little bit, involves you actually doing a much more precise measurement of a different half-life, a different isotope's half-life, using some data that we have online for you. Okay. Okay. So on Friday, I think I also mentioned this idea of growth and decay, the idea that very often you have a radioactive parent which decays into a daughter which is radioactive, which decays into something else which may or may not be radioactive. And we talk about parents and daughters and granddaughters, and using those differential equations that we started out with on Friday, you can solve them kind of iteratively. So if I have a situation where at the time I call 0, I have only what I'm calling the parent here. So I have a certain number I call N0 of species 1, and I've done some chemistry or in some way arranged things so that there are no daughters or granddaughters present at time 0. And I want to know how these numbers change with time as I watch. So species 1 is not being produced by any process. It's just decaying with a half-life characteristic of that particular species. So the rate of change of species 1 is just minus lambda 1, the decay constant for that species, times the number of that species present. Species 2 has a production mechanism. It's being produced every single time species 1 decays, but species 2 is also radioactive, and so it's decaying. So I have a production term, which is exactly equal to the destruction term for species 1, and then I have a destruction term for number 2, which is minus lambda 2 times its number. I can integrate this expression, as we've done before, and find that species 1 decays with a simple exponential decay law. I can take this solution, plug it in here, and actually solve for species 2, and what I find is its time dependence is a little bit more complicated. It depends on the initial number of species 1 times lambda 1 over the difference between lambda 2 and lambda 1 times this difference of e to the minus lambda 1t minus e to the minus lambda 2t. Okay? So let's look at a couple kind of extreme examples of situations where I have, let's go back here, a parent and a daughter. Let's forget about the granddaughter for now. So I'm imagining there are two species, a parent and a daughter, and I'm going to look at different relative values of lambda 1 and lambda 2. That is the decay rates of the parent and the daughter. So the first case is lambda 2 is stable. Okay? So imagine I have a situation where the parent decays into a stable daughter. And what I want to know is how does the number of the daughter change with time? Okay, so in this case, lambda 2 is 0. I just plug lambda 2 into the expression I had a minute ago, and what I'll find is that n2 grows with time. Okay, because what's happening is the daughter is decaying in to a stable, the parent is decaying in to a stable daughter. There were no daughters initially present, and let's verify that that's true. So at t equals 0 in that expression, e to the 0 is 1, 1 minus 1 is 0. There are no number 2's present at t equals 0. As t gets very, very big, e to the minus lambda t goes to 0. So I get n0 times 1, which is n0. So if I wait long enough, all of the parents decay into the daughter, and I haven't created or destroyed any atoms, so the number of the daughters eventually becomes what the initial number of the parent was. Okay, so that's a very simple case where the parent is radioactive and the daughter is stable. The next case, okay, so again I'm just talking about a parent and a daughter here, is very similar to the situation we just did with the Geiger counter. I'm imagining that lambda 1 is much, much less than lambda 2. And what you can think of that meaning is that the half-life of the parent is much longer than the half-life of the daughter. So in our case, we had a parent, cesium-137, which had a half-life of 30 years. The daughter, the barium-137 isomer, or metastable state, had a half-life of 2.5 minutes. So lambda 1, which is inversely proportional to half-life, is much, much less than lambda 2. What that means is e to the minus lambda 1t over the few minutes I'm doing my experiment is essentially a constant, and it's equal to 1. Okay, because t is very, very small. Lambda 1 is very, very small, and so therefore e to the minus lambda t is essentially 1. What that means then is I can simplify the expression for number 2. n2 of t becomes n0 lambda 1 over lambda 2 times 1 minus e to the minus lambda 2t. And now if I wait a while, and what do I mean by a while? I wait several mean lifetimes of species 2, or several half-lives of species 2. That means this term goes to 0, and I end up with n1, so this term goes to 0. It goes to 1 rather. I end up with n2t equals n0 lambda 1 over lambda 2. Multiplying both sides by lambda 2, I get n2 lambda 2 equals n0 lambda 1 at large times. This is what's known as secular equilibrium. And what's happening in that case is the daughter is decaying at the same rate it's being produced. Okay? So when I get into this situation of secular equilibrium, the parent is decaying into the daughter at the same rate the daughter is decaying into the granddaughter. Okay? And that's an equilibrium situation, which means that the number of daughter atoms present doesn't change, okay, because it's being produced at the same rate it's decaying. That's secular equilibrium. And that turns out to be important in a number of radioactive decay chains. In particular, a lot of the natural decay chains will have this feature in it at some point. So that's secular equilibrium. And what it means is the nuclei are decaying at the same rate they're being formed, so their net number doesn't change. It doesn't mean nothing's happening. It just means the same number being produced as are decaying. And then another situation is where it's not quite as extreme. Lambda 1 is less than lambda 2, but not so different than lambda 2. And now you plug in those relations into the equations we had before, and what you get is that the activity of species 2 divided by the activity of species 1, which is lambda 2 n2 over lambda 1 m1, is given by this expression, which I had down before. And now we imagine going to long times, and again, what does long time mean? It means that that quantity in the exponential there basically goes to 0. The argument of the exponential is large, so that goes to 0. And then activity 2 over activity 1 is simply equal to the ratio of lambda 2 over lambda 2 minus lambda 1. Now, this is a number. This is just a constant, because we're talking about two particular radioactive isotopes. Lambda 2 is some number, lambda 1 is some other number. So what that means is the ratio of the activities becomes a constant. This is what's known as transient equilibrium. It's a slightly different kind of equilibrium with the secular equilibrium. And then the fourth case is where you have a parent with a lifetime which is much, much shorter than that of the daughter. So lambda 1 is much greater than lambda 2. And what happens then is the parent decays away quickly, the daughter activity rises, and then decays away with its own characteristic half-life. Okay? So these are various situations. The basic equations are always the same. It's just a question of the relative values of lambda 1 and lambda 2. Okay? And you have homework which are going to force you to go through this and try to understand it in more detail. And one of the useful applications of all this has to do with radioactive dating. I'm sure you've all heard of carbon-14 dating or potassium-argon dating, and the way it works is illustrated here. It's not magic, okay? It's based on the physics we've just been going through. So let's imagine a very simple situation where we have a radioactive parent which is long-lived, like potassium-40 or carbon-14 or U-235 or U-238. So long-lived but radioactive parent, stable daughter. Okay. And we imagine that we have a situation where at the time we're going to call 0, we have some of the parent and none of the daughter. Okay. So NP is the number of parents. I call that NP of 0. And ND is the number of daughters, and I claim that's 0. Okay. Now, what happens as time goes on? Well, the parent decays away with the exponential decay law. So its number, NP of T, is the number of parent atoms that were there at T equals 0 times e to the minus lambda T. And I don't have lambda 1s and lambda 2s here because in this situation, the only thing radioactive is the parent. So there's only one lambda in the problem. What about the daughters? Okay, there were no daughters initially present. The only way I get daughters is when the parent decays into them. So this is like the situation we talked about the other day where you're producing a radioactive species at some rate, and the product then grows with time. And so the number of daughter atoms goes as 1 minus e to the minus lambda T, and the number out in front is the number of parents initially present. And you can see what happens. At very, very long times, this thing goes to 0, okay? And so the number of daughters becomes equal to the parent. So what that's saying is eventually all the parents become daughters. Okay, conservation of atoms. And the other conservation of atoms equation we can write down is at any particular time, I've got both parents and daughters present, but the sum of those two must be equal to the number of parents that were there at the time I called T equals 0, because I assume there were no daughters there initially. They were all parents. So the number of daughters plus the number of parents at a particular time is the number of parents that were there initially. Okay, so now I've got these three equations, and let's see what I can do with it. So from equation 1, what I'm going to do is take the natural log of both sides. Okay, so I take the log of NP of T, and I take the log of this thing. And what I find, with a little bit of algebra then, is that the logarithm of this ratio, NP of 0 over NP of T, equals lambda T. Okay? Because the natural logarithm of an exponential is just the argument of the exponential. Okay, nothing fancy there. Okay? And then I rewrite that equation and solve for T, because what I'm trying to do is I've got a rock, or I've got a bone, or I've got some papyrus or parchment, whatever, and I'm trying to figure out how old it is. Okay? And so I solve for t, which is the time the object has been sitting around collecting daughters. So t then is 1 over lambda times the logarithm of np of 0 over np of t. Now, when you look at that and think about what those numbers mean, if I wanted to figure out the age of, let's say, this bone, using that equation, I would have to know how many parents there were at t equals 0. But imagine that bone is, 1 billion years old. Okay? I have no idea how many of those nuclei were present 1 billion years ago. But thanks to equation 3, I don't have to do that. Okay? Because I've got this conservation of atoms equation, I can make use of that and plug it into the expression I had a minute ago. Okay? Basically solve for np of 0, replace np of 0. And when I do that, I get that the time, the age of the object, is 1 over lambda logarithm of 1 plus the number of daughters that are present now, divided by the number of parents that are present now. Okay? Those are things I can measure. I get the bone in my hand through some technique that we'll talk about later. I measure how many daughter atoms there are now. I measure how many parent atoms there are now. And from that ratio, I can figure out how old the thing is. Okay? That's remarkable. Okay? Because you can do a measurement today on an object you have in your hand, and you can figure out it's 1 billion years old, or whatever. And a very nice example of this technique is the potassium-argon system. So potassium-40, I mentioned earlier, it's a naturally occurring, long-lived isotope. Its half-life is a little bit more than 1 billion years. And potassium is quite abundant on Earth. So if you pick up a rock, there's relatively large amounts of potassium in it. And if you have a rock, this is a solid object in it, okay? It's reasonable to think, suppose it was a volcanic rock. So it started out as lava, very high temperatures. It was molten, and then over time it cooled and solidified. It's reasonable to think for a rock like that, there wasn't any gas in it when it formed, okay? Because whatever gases were there were released when it was molten. So if I pick up the rock today and I see gases in it, chances are those gases were created inside the rock as a result of radioactive decay. So in this case, the potassium decays into argon, and the argon, if it's a nice solid rock, will stay there. And so I pick up the rock and I do something to release the argon and measure how much argon, and in particular argon-40, which is the product of the radioactive decay of potassium-40. I measure how many argon-40 atoms there are, and I compare that to the number of potassium-40 atoms which are in the rock today, and from that I get the age. Okay? And that's done around the corner from this building in the Berkeley Geochronology Center. They do this for a living over there. Not just potassium-argon, but a number of other isotopes that all have the same properties, that you have a long-lived parent and a stable daughter that you can measure. And I think there's a homework problem you've got this week on using the radioactive decay information we have to figure out the age of an object. But this is the basis of it. Okay. One thing I think I pointed out already, and I want you to get much more familiar with it, is the fact that there's an enormous amount of nuclear data available to you online. And the best place to go that I know of in the world is a site which is made by Lawrence Berkeley Laboratory. It's called the Isotopes Project. That's the URL for it. And when you go to that site, what you'll find are links for all of these things. And when you click on each of these, you're going to find an enormous amount of nuclear data. And I'm going to assume you know about this in your homeworks, okay? So you'll often get a homework problem where a reference will be made to a particular isotope or some radioactive decay or something. And, I may not explain why it is that way or where it came from. I'm assuming you know about this and you're going to go here to find out anything that you need to know. And so, for example, one of those links over here is called the Table of Radioactive Isotopes. So I mentioned that there are about 3,000 isotopes that are known, of which only 270 are stable. So the other 2,700 roughly are radioactive, and essentially every single one of them is cataloged in that book and that website. So if you click on it, you'll see a home page that looks something like this, which has a lot of information on the people who did all the work to provide it. And one of the things you can do is, suppose you're interested in the decay of a particular isotope, or nuclide as they're called. So over there, nuclide search, I click on that, and it'll ask me, okay, what isotope are you interested in? And you'll identify it by the Z and the N or the A of that particular isotope. And let's suppose it's cesium-137 I'm interested in, which is the one we just looked at. So I type in 137.55 or 137 CS, click, this is the first thing that pops up. It says, cesium-137, its half-life is 30 years, it has a ground state spin-in parity of 7 halves plus, and then there's a bunch of other information there. And then if you want to actually see how it decays, you ask for a decay scheme. Okay? You can get level scheme, click on that, and you'll get a drawing that looks like the one I showed you earlier that I drew by hand, which I basically copied from here. So there's my cesium-137 up there with a 30-year half-life. It says that it beta decays. This number here is the percentage of the time the beta decay goes to a particular level. And what it says is that something like 94.4% of the time, the beta decay goes to that level at 661.659 keV. And oh, by the way, the half-life is 2.552 minutes. Okay, so we didn't do a very bad job measuring the half-life here. Okay. There's lots of other information. So there's something called exploring the table of isotopes. And here's a periodic table. And you click on the element you're interested in that day of the week. And let's say it's potassium. So you click on potassium, and here's a list of all the potassium isotopes which are known. It tells you what their half-lives are, whether they're stable. So here's our potassium-40 with the 1.3 billion year half-life. It tells you how they decay. It tells you the spins and parities. If they are naturally occurring, it tells you their abundances. So it says that we've got 3 naturally occurring potassium isotopes, 39, 40, 41. 40 is very, very rare. Okay? Most of potassium is 39, which is stable. Almost all the rest of it is 41, but a little tiny bit is this radioactive isotope that we use for dating. I mentioned that you have a homework problem where you're going to figure out the half-life of a different isotope, and what I've asked you to do is to go to this website, and it's a place where maybe 10 years ago we had several high school teachers from Vallejo working with us up at Lawrence Berkeley Lab. These are the 2 teachers. And what we did is we produced 6 different radioactive isotopes whose decay schemes are shown over there. They're all similar to the cesium. In fact, the cesium is one of the ones we did. They're similar in the sense that they beta decay to an excited state in the daughter nucleus, and then gamma rays are emitted. And we used a different kind of detector, a much more sensitive detector and more precise detector, shown over here. This is called a germanium ionization counter, which later in the semester I'll bring in and show you. But what it does is it measures the gamma rays that strike it, and it sorts them out according to their energy. And so you measure the energy of the gamma ray to determine which particular isotope it is that's decaying, and then you measure them as a function of time and measure the half-life. So these folks took all the data and set it up, and when you go to the website, there are a whole bunch of instructions there that tell you how to extract the half-life, and this is the kind of data you'll see sitting there. So this is one particular isotope. It's manganese-56. When it decays, you get 3 nuclear gamma rays emitted. They're highlighted, I think, in yellow. That's what these vertical bars mean. And you can use any one or all 3. And what you end up doing is, in this situation, this upper spectrum, so this is the energy of the gamma rays going this way. The vertical axis is the number of gamma rays as a function of their energy. So this spike here is a very pronounced, very high abundance gamma ray from the decay of manganese-56. In this spectrum, we started it at 10:35 in the morning on some day. I think the spectrum was collected for an hour. And we repeated the process over and over again. So here's a spectrum that we collected at 4:37 in the afternoon, so 6 hours later. And what you can see is the same 3 peaks are there, but they're much smaller now than they were initially because the thing is decaying away. And by measuring the number as a function of time, you can work out the half-life. So what I've asked you to do in the homework is to pick any one of those isotopes you want, go through the procedures that are outlined there on how to do it, measure the number of gamma rays as a function of time, figure out what the half-life is, and then compare it to the known half-life, which is on that table of radioactive isotopes website.